Hello, good morning. Today is December 18th and it's around 3:30 a.m. Dallas time in the United States. So that's Central Standard Time. And I'm giving a keynote presentation, and that's going to be December 19th in the morning around 10:15 a.m. in Bangladesh time, which is going to be Dallas time tonight, December 18th, around 10:15 p.m. And so this is a placeholder presentation just in case there is a glitch with technology when I give the keynote presentation via Zoom later this evening, which is tomorrow morning, 19th morning, Bangladesh time. So the conference is IEEE ICCIT. It's the International Conference on Computer and Communications Technologies, Information Technologies. And it's sponsored by the Bangladesh chapter of IEEE. And I'm very honored to give this keynote presentation. And I believe this is the first time I've given a presentation in Bangladesh. Although it's virtual, I'm still honored. And we have this virtual presentation because of COVID-19. And hopefully next year or in the near future, we can all meet face to face. I'm Bhavani from the University of Texas at Dallas. And now I'm going to share my screen. Okay. So my talk is going to be integrating cybersecurity and artificial intelligence with applications in the Internet of Transportation and infrastructures. So it's going to be a 45-minute presentation. So, and then there's going to be questions and answers, I believe, around 5 to 10 minutes. Okay, so the outline of my talk. Part one, I'm going to talk about integrating security and artificial intelligence. In particular, I'm going to address 4 topics: big data security and privacy, privacy-aware quantified self, data science, machine learning, AI. All of that I'm bundling together and calling it AI for cybersecurity applications. And then securing the data science, AI, ML techniques. What happens if these artificial intelligence techniques are attacked? Okay, so that's part one. Part two, I'm going to give an example of a cyber physical system and some of the security aspects. In particular, I'm going to talk about Internet of Transportation and infrastructures, and what about security and privacy for such systems. And part three is going to apply part one to part two, which is applications of security and AI for Internet of Transportation and infrastructures. And we have a number of sponsors I'd like to acknowledge, and also my colleagues, Professor Alvaro Cardenas, Professor Murat Kantarjalu, Professor Latifa Khan, who is actually from Bangladesh. He is originally from Dhaka. And our former PhD student, he's now Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so SecAI, which is integrating cybersecurity and AI machine learning data science. So I'm going to give you a bit of a motivation, okay? Data mining, security, and privacy. So I introduced the idea of the privacy violations that could occur due to data mining. So back in 1996, there were people looking at data mining for cybersecurity applications. I presented a keynote address at the IFIP 11.3 in 1996 in Como, Italy. And then I talked about all the privacy violations. We put lots of data together and mine and dig and extract those nuggets, which could be highly sensitive. And later, at Pacific Asia Knowledge Discovery Conference in 1998 in Melbourne, Australia, I published, I presented this idea again, and subsequently I published a landmark paper. I call it landmark because I was a program director at the National Science Foundation, and that was back in 2002. And so when you're a program director, of course, when you publish a paper, it gets lots of citations, and it sort of spawned a new area of research. At that time, there were researchers at the IBM Almaden Research Center, and they focused on privacy preserving data mining. They developed this whole idea. So the whole idea here is you take the original data could contain sensitive information. So you don't want to divulge the original data. And so you add some noise, perturbation, and so on. So here X prime is noise added, and now you have the modified data mining process, but then the final result should be this more or less the same. Otherwise, what's the point in doing data mining? So then when I joined the University of Texas at Dallas with my colleague, Professor Murat, we co-supervised a student, Dr. Li Liu. She did some very good work on the perturbation method. How do you perturbate the data? And what are the methods for perturbating the data? And also she looked at privacy preserving decision trees. So since then, after the IBM Almaden researchers' work, they did privacy preserving rule mining, we did privacy preserving decision trees, and there was lots of work on privacy preserving this and that, okay? So then comes 2014, now we have big data. So data mining, security, and privacy, it's all exacerbated because massive amounts of data are being collected. And we hosted an NSF, National Science Foundation workshop on big data security and privacy in September 2014 and presented the results to the Interagency Working Group in February 2015 in Washington, DC. So as a result of that, there were quite a few efforts that were being funded on big data security and privacy. Okay, so what did we do at the workshop? What did we find? So we said, due to technological advances and novel applications, it's now possible to capture and process large amounts of data for various tasks, right? It could be for disease outbreaks, homeland protection, financial analysis, healthcare, drug discovery, right? Even for cybersecurity, right? Cybersecurity like anomaly detection, intrusion detection, insider threat detection, and so on. So whatever data you collect, even if you anonymize by removing identifiers, you can put the various records together and infer something that is highly sensitive or highly private. Okay, so even some security tasks, right? You need to collect lots of data, like for authentication, you may need multi-factor authentication, some private information. So this information, if it's misused or stolen, can lead to security breaches, right? So some of the directions include securing the data, access control models, privacy enhanced techniques, big data analytics, machine learning for cybersecurity. And one thing I haven't mentioned, which I'm going to discuss in this presentation, what happens if these machine learning techniques are attacked? It will be devastating, right? So that's something, because everyone is using machine learning for finance, machine learning for healthcare, and so on. So that's a very important area. Okay, so privacy-aware quantified self, this is something social scientists and psychologists have come up with in the sense that we are collecting data, our glucose readings, our blood pressure, our Fitbit data, everything is collected to give advice so we can have a better life. That's the quantified self movement. So we can have better habits. Like, wouldn't it be great when I open the refrigerator, right? Because I love chocolates and vanilla ice cream. And so the refrigerator is going to tell me, no, you cannot eat chocolates. Stop taking those chocolates, right? But in order for it to do that, lots of information have to be collected about me. And what if that information is sent to my insurance companies, my healthcare insurance? Then the insurance could be denied, right? Saying that, oh, this person is eating so many chocolates, she could get diabetes, right? So data collection and sharing sometimes is being carried out without the user's knowledge, right? So data collected by device monitoring blood glucose levels, if it goes to the wrong hands, then they might deny not only myself coverage, my parents, my siblings, my children, my grandchildren. So privacy violations could easily get out of control if these data collectors can aggregate various financial and health data and the tweets and Facebook and so on, and they could sell this information. That could be quite dangerous. To address these growing challenges, we need privacy-aware quantified self. So what are we proposed, or what are we developing? A policy-based. Policies are at the heart of our approach. Policy-based, privacy-aware quantified self. So here we have our cell phone or smartphone, and it's going to collect healthcare, fitness, location, social media, images, all other sources, right? And so we have data collection, data storage, data analytics, data sharing. And from here, we encrypt some of the data. It's stored in the backup storage, and some of the other data is anonymized, and you have cloud-based services. And now you have privacy-aware quantified self-manager running on this mobile device. And so what we are saying is policies have to govern what data should be collected, how should data be stored, which data should be stored in the cloud, how do you carry out analytics, and how do you share the data. So that is at the heart of our approach. So here you have our sort of smartphone and the cloud to store some of the data. Some data could be encrypted. So again, as more and more data is collected, some of the data could be in a smartphone, some could go in the cloud, but policies have to govern. And then based on access control policies, some of the local apps could have access to the cloud. In some cases, you may not need all of the data, right? You don't need daily weight of a 20-year-old person. But for a 70-year-old person, you may want to get the daily weight, right? So in other cases, data may have to be deleted to preserve privacy, but what does it mean to delete the data, right? So sometimes, you may have to generate some fake locations, and is the data really getting deleted? So you need audit policies. We envision data sharing and analytics will be carried out using services in the cloud. Again, what are the policies? And again, based on different scenarios, some data could be encrypted and some data could be raw, right? So everything has to be governed by policies. So that's our part on the information I'm going to talk about on privacy. And we have presented a paper at the ACM SACMAT conference on this work. So the next topic is data science for cybersecurity applications, right? So we are looking at data stream classifications, and this work is with Professor Latifa Khan, who is one of the top experts on data science for cybersecurity applications. So he's really one of the top experts in data science, as well as he's very good in cybersecurity. So he applies one to the other. So you can use past data to build classification models. Yes, that's the normal procedure, right? So and then you predict the labels, right, future instances, and it helps in decision making. So about 20 years ago, right, we were doing a lot of work. We developed one model. But today we have massive data streams continuously coming, very common in our connected digital world, massive amounts of data. And so one classification model is not enough. You need an ensemble of models. So several models here, right? So because today it can say by Microsoft, tomorrow by Facebook, day after tomorrow is going to be by Apple, the next day is going to be by Amazon, and then IBM, right? Things are changing, concepts are changing. So one classification model is not sufficient. So you develop a collection of models, but then what happens? You can't keep all the old models because they're outdated. You've got to throw the old models. And what do you mean by throwing the old models? So throwing the old models mean these ensemble of models have to work together and decide which models to throw away. And sometimes you may need human in the loop. So when the test data comes in, these models talk to each other. And then if it's attacks, you block and quarantine. Otherwise, you store it in the server. That's a simple idea. And we have applied it to insider threat detection. Okay, so inside a threat, there are bad people who are pretending to be good people, right? There are people who carry out espionage and give out all kinds of secrets, but they are pretending to be good people inside the organization and giving all of the information to the adversary. And the organization has absolutely no idea. Similarly, the processes in the system pretending to be good processes, some application process, or it could be database process. So you have absolutely no clue that, no suspicion that these processes are bad processes. And so these processes, some of them malicious code is going to look stay inside and steal the data and send it to the perpetrator. So we have designed and developed ensemble-based stream mining algorithms. We will look at supervised learning. It's one class supervised support vector machine as well as support vector machine. And then that supervised, unsupervised, we use graph-based anomaly detection. Okay. So in unsupervised learning, we use some compression-based techniques to make it more efficient, to model common behavior sequences. And the results, so we have compressed dictionaries. So our papers describe the techniques that we have used. So it results in a classifier with substantial accuracy increase. And then, of course, we develop an ensemble of classifiers and we throw away those classifiers that are outdated. So here's our architecture. And so you have this collector, the operator is going to collect all of the data like system calls and various kind of patterns. And sometimes with unsupervised learning, you don't even know, right? So anyway, you get all this data. So you've got the I chunks, and then you develop an ensemble of models, extract all these features, and you learn one class support vector machine and then support vector machine, or graph-based anomaly detection, which is unsupervised. Ensemble of models, old models are thrown away. And then when the I+1 chunk comes in, extract features, and then ensemble of models work on it. And then is it an anomaly or not? Okay. So again, the strength here is in the ensemble of models and the algorithms we are using, such as support vector machine, one class support vector machine, and the graph-based anomaly detection. So this just one example inside a thread, but we can also apply it to a number of other applications, such as anomaly detection, malware analysis, and so on. So that part is, right, as I said, applying data science for cybersecurity. Now comes the difficult part, which is one of the most popular areas right now in cybersecurity. What happens if the data science techniques are attacked, machine learning, right? So, and we are depending on this, not just for security, we are applying this for everything, for marketing, for sales, for manufacturing, for healthcare, for drug detection, for COVID-19, for financial analysis, you name it, we are using AI. If these AI techniques are attacked, so adversary is, and this is with Professor Murat Kantarjalu, my colleague. So adversary is modifying our data to defeat our algorithm. So adversary is trying to thwart us, and we are trying to understand the adversary. It's not concept drift. It's not online learning. Adversary is adapting to avoid being detected during training time, during test time, modifying features when data mining is deployed. There's a game that is being played between data miner and the adversary. So we both play games. So here's the idea. You have these red squares, which are bad instances, and the blue circles are good instances. And this is a support vector machine boundary. So the red squares are trying to get in here. So what these bad people are doing, bad instances, trying to push, see what happens. They are trying to push the red squares into this location so they will not be caught. A support vector machine algorithm will say these are good instances, right? So we have to in time figure out what the adversary is doing. And so it becomes sort of a game playing between the adversary and us. Okay, so what do we do, right? Before we go to what are we going to do, we want to look at the types of attacks. So in theory, the adversary can, look at any attack. All he or she has to do is to get in one tiny way. And we have to cover everything. But again, we cannot cover all possible attacks today. So we are looking at some classes of attacks. Of course, some say, if you're only going to do some of the attacks, right, consider some of the attacks, what's the point? But I say something is better than nothing. Because if the adversary is trying that particular attack, then we have a solution. So we are looking at two types of attacks, right? The attack model, a free range attack where adversary can move the malicious data anywhere within this particular domain. I won't go into the details. It's in our paper published in the Knowledge Discovery ACM KDD conference. And then the other model is more targeted. Adversary can move malicious data closer to the target point, right? So these are the types of attacks. What do? what we are trying to do. So here the red squares are the bad instances, the green circles are good instances. So this is a original support vector machine boundary. Black dashed line is the standard support vector machine classification boundary, and the blue line is the new boundary, adversarial support vector machine classification boundary. What we are trying to do is to take these dashed lines, and we are doing some mathematical computations and moving it here to the blue line. So that way, what's happening by moving it, some of these bad instances that the adversary is pushing up here are going to be caught as good instance. Bad instances, some of these adversaries trying to push here to pretend it to be good instances, but we know that they are bad instances because the blue line is here. And here's a better idea, because the red crosses are bad and the black is also the bad, the green are the good stuff. But then by moving this, you can see a lot of the bad instances that the adversary is trying to push, pretend to be good, we are catching it. So you can ask the question, what about pushing this blue line right here? If we push the blue line right here, all of these bad instances would be caught. But guess what? The green instances, which are good instances, will come out as bad instances. So we don't want false positives and we do not want false negatives. So that's where we do a lot of mathematical calculations using game theory and so on. We have to move it to an appropriate position. That's the challenge. So a threat model, as I said, test time, deployment, attacker modifies X to X prime, modify packet length by adding dummy bytes, add good word to spam email, and add noise to an image and so on. Okay, so this finishes my part 1, which is integrating cybersecurity and AI. So I talked about privacy, then I talked about AI for cybersecurity, and then what happens if the cybersecurity techniques are attacked. Okay, so I have talked for about 20 minutes and now I have around 25 minutes and I'll finish it in 25 minutes. Okay, so security and privacy for the Internet of Transportation and critical infrastructures. So we know Internet of Things, cell phone connected to the television, connected to the refrigerator, connected to the lights, connected to almost everything, right? That's Internet of Things. That's Internet of Medical Things, your medical devices and hospitals and all, everything is connected. Internet of Transportation is that all the vehicles are connected, they're connected to the trains, to the trucks, and to the roadworks, and that's ground vehicles. You also have sea vehicles, all the ships coordinate, the aircraft and the drones all coordinating. Sometimes you've got to have coordination between the ships and the drones and the aircraft and the vehicles, the ground. So like for instance, if you are going to have, say, in a military situation, you have Army, Navy, and Air Force, right? The Air Force is aerial, and the Navy is sea, and the Army is land. They all have to work together and connect. So you've got the Internet of Transportation systems, right? So what is Internet of Transportation? It's an Internet of Things, special type for transportation, autonomous vehicles, AVs. They improve day-to-day activities, safe driving, delivering stuff, delivery packages, improving traffic, and so on. And in the US alone, trucks alone in the US carry 63.3% of the freight of goods. AVs, as I said, not limited to ground vehicles, also sea and land. And there's a level of automation. It can go from 0 to 5. And the ground vehicles, the level of automation is not that great. It's about partial automation, level 2, but aerial vehicles, it's at level 4. Companies are investing heavily in AVs, and General Motors spent $728 million in R&D in 2018, and with plans of increasing to $1 billion in 2019. While there's a lot of potential, right, in AVs and the improvements it can do to the transportation industry, security and privacy concerns pose new challenges. Right. So again, for this number, that was in 2019. So I should get the actual number, and 2020 is almost done in 10 days, right? So anyway, or actually 12 days, right? So while there's great potential, AVs and the improvements, but the huge problem, security and privacy. So security autonomous vehicles, AVs will evaluate their environment, all these sensors, right? And variety of sensors like cameras, GPS, inertial measurement units, and LIDAR, radar, ultrasonic sensors. So some previous research has shown that sensors are susceptible to malicious tampering, like IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. So what do we have? AVs rely on sensors to evaluate and interact with their environments. Sensors, as we said, susceptible to GPS spoofing and transduction attacks that manipulate environment physical signals like visual, sound, magnetic, and so on. And then some of the traditional security, memory management, cryptography, and so on, that's not sufficient because it's a real-time nature. Real-time constraints and sensors are really tiny. They may not have a lot of memory, right? So a lot of those aspects have to be taken into consideration. So what have we done? We have developed a physics-based anomaly detector. What do we mean by physics-based anomaly detection? We take the physical properties, the moments of inertia, the mass, the velocity, and all of those properties, right? And we build a model. And then, so here's our algorithm. So we built a reference monitor. Reference monitor is that part of the system that is security critical. So absolutely the reference monitor has to be small as possible because you want to reduce its attack surface, and it has to be secure. So physics-based anomaly detection algorithm for ground and aerial AVs. The algorithm will consist of 3 parts: building a model offline of the AV's physical invariance, right? Offline, implementing an online tool to monitor expected and observed behavior to detect anomalies, and raise an alarm if significant residual difference exists. So offline pre-processing, online verification, and anomaly detection. It might sound like any other sort of intrusion detection algorithm, but the challenge isn't the data. It's not any data, right? It's the control systems data, right? Sensor data, right? It's not sort of network traffic. So, and it's also got a physics-based model. So that is the challenge here. So, and this work, by the way, is with Professor Alvaro Cardenas and our joint student, Dr. Raul Quinones. So we have M is mass of vehicles, D drag factor, B is the thrust factor, moments of inertia, and so on. So offline processing, the AV's autonomous vehicles invariants are calculated using a well-known linear model for aerial and ground vehicles. And then we use the accelerometer, gyroscope, and magnetometer sensor data. Okay, all sensor data, they are the X, Y, and Z axis is used for the aerial vehicle. And then vehicle position and steering angle is used for the ground vehicle. So online stage, remember, stage 1, pre-processing, offline. Stage 2, online. What do? Extended Kalman filter is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor inputs. Okay, that is the estimating unknown parameters. And then that's the online stage. And then, okay, the algorithm then is divided into 2 sections. So extended Kalman filters have been around. Control system researchers and electrical engineers have been using it for a long time. So, but again, the challenge is in developing this model. Algorithm is divided into 2 sections that predicts and corrects estimation before it's compared against the sensor data. Anomaly detection, we use the CUSUM algorithm is used to detect persistent attacks, and it's in the literature. An alarm is raised if the residual difference is larger than a predefined threshold. Okay, so what's our implementation? We only work for drones and the cars. We didn't do sea, right? We don't. I mean, we do have lakes and so on in Dallas, but we don't have, big oceans here. So, aerial AV, Intel ready-to-fly drone. That's our aerial device. Controller is PX4 flight controller, focused on detecting GPS spoofing and gyroscope attacks. I just want to make sure I know the time. Let's see. Just a second. Okay, the gyroscope attacks. And GPS attacks are detected after 0.2 seconds, GPS spoofing, while gyroscope attacks are detected after 1.5 seconds, and the overhead is about 5.4%. The ground AV, custom built on top of Traxi Ford Fiesta, controller is ROS Kineticam, focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds. Overhead introduced is about 2.25%. Each threshold produces a probability of false alarms of about 2%, and we have to reduce it even further. So that's the physical implementation. Okay. What about privacy? We cannot forget about privacy, right? So we looked at security, but beyond security of the vehicles, transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors, lampposts, surveillance cameras to help identify. But without a doubt, AI is very, helpful, and surveillance is really useful. We can figure out who is speeding, what about traffic jams. However, from a user point of view, it's quite dangerous because there are privacy concerns from all information needed by such system that could lead to private information being exposed, such as vehicle identification and driving patterns, right? I don't want people to know that I'm an erratic driver, right? Or I don't want people to know where my location is. Or if I'm a smoker, of course I'm not, but I don't want people to know that I'm smoking in the car because somebody will send it to my insurance company and then they will charge me higher premiums, thinking that I might get lung cancer. Anyway, legislators, engineers, but then we also have to collect this data. So, and I'm going to talk about it later. Legislators, engineers, scientists should keep privacy concerns in mind as advances in IoT become prominent in day-to-day activities. This will aid in improving public perception, reduce hesitation from consumers, and increase the adoption rate of new technologies. Okay, so the main thing here is that the legislatures, engineers, scientists, they all have to work together. So again, policy aware data collection, data sharing. So I'm going to talk about it in the next, in a few charts. Okay, so we finished. I've got around about 12, 13 minutes. So I think the time wise, we are doing well. So part 3, applications of security and AI for Internet of Transportation and Infrastructures. Okay, so how do we apply part 1 to part 2? So data science AI for transportation security. So Internet of Transportation systems are subject to attacks like any cyber physical system. And that's what we have been talking, right? So we got GPS spoofing and so on. Again, streaming data is being collected. Data is coming from all types of sensors, right? Millions and millions and millions of sensors in an IoT device. So including autonomous and in the future, driverless vehicles. As transportation systems go electric, we need energy conservation. Threats to the security of systems could cause massive damage, including accidents, loss of lives. What happens if you're stranded in lonely highways, if they attack our energy system, right? Data science ML techniques, we can maybe complement, right, the Kalman filter algorithms, or maybe just rely mainly on machine learning techniques. So the question is, can stream analytics be applied to say that we have applied for financial and telecom data? Can we apply it to transportation data? And the main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, so how do we combine, say, the Kalman filter with machine learning to apply, or augment Kalman filter, or just apply machine learning? So that's future research. So that is one point. Another point is, what about adversarial machine learning? So we said Internet of Transportation systems, right? These systems are going to depend heavily on data science, AI, ML techniques for various applications, including optimum directions, driving without a human in the loop, and many more things, right? So there is this adversary, right? So we are using, without a doubt, AI is something we absolutely need, not just for cybersecurity, but for giving directions, for preventing accidents and autonomous vehicles, right? And driverless cars, right? We need for all the coordination between the trains and the trucks. And even when we talk about the air and sea and land vehicles, everything has to be coordinated, right? So that's why we really need AI, right? For many industries, including the transportation industry. So we have this adversary, right? Adversary is going to learn all the AI models used by the vehicles, as well as learn about the data being used to train the models. It could try and poison the data. It could try to thwart the vehicle's learning process. Imagine the learning algorithms have to adapt to the adapt and thwart the adversary's actions, because if the adversary is going to poison our data and if it's going to thwart our algorithms, it's going to be a disaster. So the algorithm, right? The learning algorithms have to adapt to thwart the adversary's actions. Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithms, right? So they both play games. Just like I mentioned earlier, adversaries try to find out what is it that these vehicles are doing, the machine learning models that are being used to prevent the accidents. Adversary is going to thwart those models, and then accidents could happen. So we have to figure out what is the machine learning models, what is the adversary up to. So it becomes game playing. What type of game? Is it zero-sum game? Is it Bayesian game? We have to understand the data. Understanding the data is essential. And research on this topic is just beginning. Okay, so it is really something, this is like one of the hottest topics, right? As I said, adversarial machine learning. How do we bring that to cyber-physical systems, in particular, the Internet of Transportation systems? Okay, now comes the privacy part, right? Remember I showed you our smartphone that we have data collection, health data, social media data, and various Fitbit data and so on. And the smartphone is getting all the data and looking at policy aware data collection, storage, access, analytics. Can we, I'm putting a question mark, can we apply something, do something similar for Internet of Transportation? So instead of healthcare data and so on, we are getting radar data, GPS data, cameras, LIDARs, ultrasonic sensor data. All of that is here in some small gadget, because it can't carry, you can't put a big computer in here, right? Small gadget. So data collection, data storage, analytics, and so on. Some of the data goes into the cloud, some sort of cloud-based services, some could be anonymized. And what data should go to the cloud? Again, the key point here is that policies have to guide the data collection, data storage, access, analytics sharing. Without the user knowing, you cannot collect data about the user's location or the user is smoking, so the user has to be aware, right? So those are some of the things that we have to be focusing on. So the point when I say about policy is that we cannot sort of simply work on toy policy, TOY, or children's policies. Like John is telling Mary, I'm going to tell you a secret, but Mary cannot tell the secret to Jane, right? But that's like children playing a game. So we have to, and we are computer scientists, right? So we really don't know as much about policies as the policy experts. So we are working with policy experts, right, to come up with the appropriate policies so that we can look at data collection, storage, and analysis. So that's really our challenge. So that's one thing. So that sort of finishes applying part 1 to part 2. So we get part 3. One other thing I wanted to mention, I have around 5 minutes left. So what about trustworthy analytics? So one way is, of course, we bring machine learning, but we said, can these machine learning techniques be trusted? Meaning that these machine learning techniques be attacked. And that is such a big problem, because remember I showed the types of attacks. We are only handling 2 types of attacks, right? We are handling the, the free range attacks and the targeted attacks. But in reality, we could have hundreds of attacks. So is there any alternative? Because we cannot handle all those attacks. So what about trustworthy analytics, right? So computations over big data may require massive computational resources, and organizations, automobile companies could use third-party service to outsource some computations. So third-party servers are used for computation. Data becomes available in untrusted environments, either observed by man in the middle during data transmission or inside a threat from adversaries, third-party location where computation is performed. So in these cases, data owners may need to protect their data and require cryptographic guarantees about data security and integrity of computational output from these third-party services. We are conducting research in secure encrypted stream data processing and trustworthy analytics using advancements in embedded hardware technology. So Intel has come up with an SGX platform, right, to carry out trustworthy analytics. It supports trusted execution environment. So the whole point with Intel is that, I'll show you the picture. So need to explore the applications to Internet of Transportation. Okay, so we haven't looked at it for Internet of Transportation. This is the Intel's platform, right? So you have users to secure connection. We have application memory, runtime, SGX runtime library, some wrappers, some encrypted code, and all of the data analytics is being carried out, right, in this SGX enclave memory. So it's all in a sort of a securely carried out. Now, we have done a lot of work using this SGX platform, but there are some articles that are coming out saying that there may be some issues with this SGX platform, and that's something we are going to look into it further. But so far, we've gotten some good results, and it appears to be secure, but we need to, as I said, we need to do more work in this area. But this is something, if it all works out, it'll be great because a lot of the machine learning techniques could be executed in hardware and protected. So this way, if it's executing in a protected domain, right, in the SGX environment, in the platform, then they may not be attacked. So that is one of the solutions that's being explored. Okay, so now we have again 3 minutes. So this is my last chart and summary and directions. So lots of developments in security and AI, integrating cybersecurity and AI. It's exploding. Data science, machine learning for cybersecurity, and of course, machine learning for almost everything. Of course, applications of AI for security like insider threat detection. And then I also talked about security for AI, adversarial machine learning, right? Adversary, the machine learning techniques are going to be attacked. And then what about privacy, right? Privacy-aware healthcare and managing one's life's activities, privacy-aware quantified self, right? So lots of data being collected. And so we are saying policies have to govern the data collection, data processing, and so on. At the same time, with the development of Internet of Things and Internet of Transportation systems and infrastructures, security and privacy solutions are being developed, and these are mainly physics-based solutions. As driverless cars become a reality, more and more of the AVs will use AI ML techniques, right? So we came up with some physics-based solutions, developing a physical model, and then coming up with using Kalman filters. But then as we use more and more driverless cars and so on, we'll have to use AI ML techniques, right? But then these AI ML techniques could be attacked. How can we bring AI solutions for the security to detect these security attacks? And what happens if the AI techniques themselves are attacked, right? And of course, AI can be used for the Internet of Transportation, not just for security, for a number of applications, right? For coordinating all the vehicles, making sure there are no accidents, and so on. And then I talked about a privacy-aware, policy-based data management framework. What we are developing for quantified self can be applied for Internet of Transportation. So private policy-based data collection, data sharing, and so on. And then what about trustworthy analytics? Can we use this Intel SGX platform or similar platforms to do the machine learning in hardware? And there are numerous opportunities exist for substantial research in this area. And as I said, I've got to thank Alvaro Cardenas and Dr. Raul Quinones, that's our former PhD student. So they worked on the Internet of Transportation and security. Dr. Murad Kantarjulu, he did a lot of work on adversarial machine learning as well as data privacy. Dr. Latifa Khan, who is from Bangladesh, he is a PhD from University of Southern California, is a top-notch researcher and professor. And he is working, he's done a lot of work on data science, machine learning, AI for cybersecurity. And Ms. Rhonda Walls is our project coordinator, and she sort of helps us and keeps us all grounded and supports all of our activities. So I'm going to stop sharing, and I think this is about time for questions. And so, so since we have, a few minutes, so at this time, I think if we are going to use the recorded presentation, of course, we'll be cutting it at this time, but I hope that there'll be no technology glitch and I can give this presentation live. But again, the main point is, without a doubt, artificial intelligence is exploding, right? And it's very real because of deep learning and so on. It's not the AI of 1960s 60s and 70s, 80s, 90s. So right now with deep learning and novel AI techniques, it's being applied for all types of applications, even COVID. And I don't know much about the COVID-19, mRNA vaccines, but I'm sure AI techniques, very likely, I shouldn't say I'm sure, AI techniques would have helped with the development of these vaccines. So for almost everything, we need AI. What happens if these AI techniques are attacked, right? So can we then trust these vaccines? Can we trust these, the financial codes, like when they say buy Microsoft today, can we really trust? Or buy Google, can we trust, right? So these AI techniques are going to be attacked. So we need to come up with secure AI techniques. And so one way is this adversarial machine learning, what I mentioned, and perhaps executing the AI techniques in the machine learning techniques in hardware. So that's also another approach. And then the last, and then how do we apply it to the Internet of Transportation systems, right? Internet of Transportation, again, is Internet of Things, but applied to transportation. It could be land, sea, and air vehicles, autonomous vehicles. And so we talked about security attacks on these autonomous vehicles. What are the solutions? What about privacy? So that was sort of a part two. Then we applied part one to part two and said part two was sort of, we use Kalman filters for detecting security attacks. So what we are saying for part three is, can we bring in some of our AI techniques and apply them for security attacks, right? And what about adversarial machine learning? What about privacy aware? The car is collecting all of the data collection, data analytics, and so on. So policies have to govern, and we've got to work with policy experts. So essentially, there are numerous opportunities, right, for lots of research. And I hope I have given you all sort of a snapshot of, what are some of the key areas and key aspects. And so that, we can all continue to work on this together. We need the entire world to work on this research area, integrating cybersecurity, AI, Internet of Transportation, so that we can come up with viable solutions so that we can have a safe world. And again, thank you very much. And again, as I said, when this is being given live, and I'll be there to answer questions. Thank you.